thanks to the Lodha Genius Programme for having me here. So actually I'm really excited to present this topic to you, school students, because this is typically a topic we present to postgraduate PhD students. So this is something I used to present at the Bangalore Microscopy course. So what I want to do today is to take you through the history of optics and microscopy. And in that process, tell you a little bit about basics of microscopy, right? Now to understand optics and microscopy, you need to understand a little bit of physics, right? So I want to start with an introduction to physics and maybe a little bit of fun. Usually you think these two things don't go hand in hand, right? So let me take the liberty of letting Sheldon Cooper tell you.
What is physics? Physics comes from the ancient Greek word physica. It's at this point that you'll want to start taking notes. Physica means the science of natural things, and it is there in ancient Greece that our story begins.
Ancient Greece?
If you have questions, raise your hand. It's a warm summer evening, circa 600 BC. You've finished your shopping at the local market, or agora. And you look up at the night sky, and there, you notice some of the stars seem to move, so you name them Planetes, or Wanderer.
So as Sheldon pointed out, our journey in physics probably started in the agoras of ancient Greece. The philosophers and thinkers of that time, they looked up the night sky and they wondered how do some of these celestial objects move. So how things move is something that always interested them. And this is a branch of physics called mechanics, right? They also looked up at the night sky and wondered how do some of these celestial bodies produce light, and more importantly, what is light? And this is a branch of physics called optics. So optics and mechanics were probably the first branches of physics. Mechanics was easier to study because you could drop a stone, make one object hit another, roll a wheel. There are hundreds of experiments that you could think about, but studying optics was more difficult. Why? Because unlike objects, you cannot touch, feel, or handle light, right? It's not something that as tangible as objects. So then how do you study light? How do you study optics? You study light by studying its interaction with matter. And there are several ways in which light interacts with matter. And one of the simplest ways is reflection, right? You all know what reflection is. And reflection follows what is called as a law of reflection. Maybe the simplest equation in physics. Angle of incidence is equal to angle of reflection. You cannot have an equation simpler than that, and probably the easiest to understand. So how many of you know the law of reflection? Almost all of you, right? Very nice. So can you tell me who discovered the law of reflection? Yeah, so it's believed that it was Archimedes, from the Eureka fame. He's the one who discovered reflection. So Archimedes discovers reflection. He builds some high quality mirrors, and then it is said he put these mirrors to very good use. So it is said when Greece was attacked by Rome using a flotilla of naval ships, Archimedes built this large concave mirror using a series of plane mirrors. He focused sunlight and burned the ships. So he built like a laser weapon kind of a thing. So did he really burn the ships? We are not exactly sure, but in MIT they tried to replicate this experiment. So under some conditions, you might have managed to create a fire. But what would have really happened is, a contraption like this would have, frightened or confused the enemy and giving Greece some advantage here. Now there is something interesting here. These mirrors are not held on posts or pillars. Can you see that? These are held by humans, most likely soldiers, right? And that means the mirrors can be moved. And this has two advantages. First, the focal spot can be locked onto the target. It's like a modern, high-end defense system that can lock onto the target. So they can lock the focal spot onto the target. And the second most important thing is they can make sure that this focal spot is as small as possible. So for a given amount of light, if you make the focal spot small or as small as possible, what happens? Exactly, the intensity of light increases at that point, right? And in modern terms, this is called adaptive optics. So the visual input received by the soldiers is processed by their brains to give a feedback to the mirrors, and this minimizes the focal spot. And if you think about this, this is a very interesting idea which is used even now, more than 2000 years later. We are using exactly the same idea to build some of the world's most sophisticated optical systems. So this is the European extremely large telescope, which is nothing but a huge concave mirror created out of little plain mirrors. Each mirror can be gimbaled following a feedback mechanism to give this concave mirror as sharp a focus as possible. Now the adaptive feedback system here is a little bit more complex. It is probably built into the tertiary mirror of the system. Now talking about telescopes is probably not what I wanted to do here, but it is worth mentioning here that optical systems are typically divided into two categories: telescopes and microscopes. Telescopes like these are built using reflective optics. You have mirror-like systems. And microscopes are typically built using refractive optics. You have lens-like systems. There are some exceptions though. So if microscopes are built using refractive optics, you need to know a little bit about refraction. So what is refraction? Refraction is an interface effect, right? When light passes from a medium of one refractive index into another refractive index, it bends. And how does it bend? Yeah, if it goes from a denser to a rarer to a denser medium, it bends towards the normal. And if it goes the other way, from a denser to rarer, it bends away from the normal. This is something you all know, so I'm not going to spend a lot of time talking about this. And the law that governs this is called the Snell's law. You also know this, right? So again, I don't have to spend time on Snell's law. So who discovered Snell's law? Snell. So Snell's law is attributed to this Dutch scientist Willibald Snellius, but Snell's law itself was known at least 400 years before Snell. So Snell made this law popular, he refined it probably, but he was probably not the one who discovered it. So who discovered it? We will take a look at few options later in the presentation, so stay tuned. Now, I want to take you to a remote village in Philippines, where this man will tell us how to put refraction to good use. So he's not famous like Sheldon Cooper or Archimedes, but in his village they call him the solar god. So listen to what he has to say. Please read the subtitles.
Siyempre, alam mo naman, ganitong lugar, squatter area, tabing release, dikit-dikit ang bahay.
Madilim talaga rito sa lugar ko na to.
Wala kami dito sa loob, lagi kami sa labas. Nadadapa kasi madilim, yung dadaan mo, hindi mo alam, may nakaharang.
Tutulog na lang ako, wala ilaw eh.
Ang tawag nila sa akin dito si Mang Dimi Solar. Napaliwanag ko yung mga bahay niya na madilim. Bubutas ka ng yero, lalagay mo yung bote, lagyan mo siya ng sealant, bago lagyan mo siya ng tubig na mineral, lalagyan ng sunrocks. Bago kabit mo sa bahay, lagyan mo sealant mo para hindi tumulo. Gawin lang kasimple yun. Dati yung ganito, tukadilim ng bago ko pagkapitan. Ngayon, nung kapitan ko na, ito na ang liwanag niya. Ito na ang liwanag.
Pumilip po ako kasi bote lang, tubig. Maliwanag na yung bahay mo.
So what happened, or what is being described here is very clear, right? I don't have to explain it to you. But you might have one question. They cut a hole on the roof, right? So why not leave a sheet of plastic or a sheet of glass to let the light through? Because this is something you have seen in some buildings, right? You have little holes with a transparent glass on top. But what difference did sticking a bottle filled with water through that hole make? So the answer to that question are two words: numerical aperture. So numerical aperture is an extremely important idea in microscopy, and we will look at it in some of the later slides. Now let's assume there was no bottle, right? There is just the hole. So whatever light comes down into that little hole gets collected by the hole. Now when you insert the bottle look at the top of this bottle. It has this conical shape, right? And this conical shape acts like a lens. And because of the lensing effect, you start collecting light from a much wider angle. So earlier it was like this, now it is like this. So much more light gets collected, or in other words, the numerical aperture, the light collecting ability of this optical system is much higher. There is something more that happens. After the light gets collected, it gets channeled through this bottle like an optical fiber, and then it gets scattered all around the room because the water you use is not really pure, right? So it gets scattered around the room. Without the bottle, whatever light gets collected comes down more or less like a shaft of light. Again, something that you would have seen. If you have a little hole on the roof, you see the shaft of light coming down. But here what you have is this optical system allows you to have this nice flow of light from outside into the bottle and then all around the room, really simulating the effect of a light bulb. So when I was looking at examples of putting refraction and scattering to good use, I could not find a better one. Now there are a couple of things that this teaches us about making a lens. Yeah? First, let's look at the material here. Water, plastic. What can you tell about the refractive index? It is higher than the ambient. So ambient is air. So to make a lens, you need a refractive index higher than the ambient, right? So in this case, water and plastic works. Imagine you need to build a lens system inside water. You need a material that has a refractive index higher than water, right? Second thing, and probably more important, is if you look at the shape, there is a gradient to the thickness, right? So you need a shape for the lens that has a certain gradient. What I'm trying to say is, if you take a slab of glass, it is uniformly thick, right? You can refract light, but you cannot focus light. To focus light, you need a shape that has a certain gradient, and the most commonly used shape is this. What is this called? It's called the biconvex. Yeah, it's called the biconvex shape. Now at this point we can ask an interesting question. Why is a lens called a lens? Any idea? Lens is called a lens because the shape resembles an object that, at least in India, we encounter it every day. I'm sure you have encountered it, of course, today. That is lentils, dal. If you take a bean or one grain of dal, it has this biconvex shape, right? And that is where lens gets its name. And if you're not convinced, does anybody know what is the scientific name of the dal that we use? Lens culinaris. So lens gets its name from lentils. So now we know a little bit about lens, so we need to know how it works. So this is something you know. If you send in a parallel beam of light, what happens? Yeah, there is a question there. Oh, that is to prevent fungal growth. So imagine you would keep it for a long time. There will be some bacteria or fungus that grows, right, just to prevent, so that the water remains transparent. So if you have a parallel beam of light sent into the lens, then it gets focused at the focal point. And the distance between the lens and the focal point is called the focal length. Yeah, this is something that you all know. But something that sometimes is not very intuitive is, what if at the focal point, I keep a tiny source of light, maybe a small LED is kept at this point. LED will radiate in all directions, and a cone of that light is intercepted by the lens. Yeah. So right now, the light is going in this direction. How will the light come out? It will come out parallel. Very good. So this means that what happens in the forward direction can be traced back in the reverse direction. And this is mostly the case. There are some exceptions though. So when you design an optical system, this is something you might want to keep in mind. And this is, if you're taking the microscopy project, this is one concept that you have to keep in mind. Now there is something a little bit counterintuitive about a lens. I don't know if you have noticed this. At the center of the lens, it is the thickest, right? So there's a gradient. At the center, it is thick. As you move from the center to the periphery, the thickness decreases. And at the periphery, at this point, it is the thinnest. But if you look at the light behavior, the light that goes through the center does not bend. As you move from the center to the periphery, thickness decreases but bending increases. Did you notice that? This light beam that is passing through the thinnest part of the lens is bending the most. And the light beam that is passing through the thickest part of the lens is not bending at all. Is that counterintuitive? You would have probably expected that a thick piece of glass will bend more and a thin piece of glass will bend less, right? So what is happening here? Now let's take a look at the Snell's law. Snell's law does not talk about thickness. So refraction is independent of thickness. It depends only on two things, the refractive index difference and the angle of incidence, right? So maybe we want to look at it in a little bit more detail. So we have this giant lens here. So let's see what happens when you have a light coming in and hitting the center of the lens. So here light is going from a rarer medium to a denser medium, but what is angle of incidence? Angle of incidence is 0. So it doesn't matter what is the refractive index difference, because angle of incidence is 0, angle of refraction is 0. Now it proceeds to the next interface, which is a glass-air interface. Same thing happens, doesn't matter what is the refractive index change, because angle of incidence is 0, angle of refraction is 0. So that is the reason why the light passing through the center of the lens, the thickest part of the lens, does not deviate. Is that okay? Now let's go a little bit up. At this point, the angle of incidence is not 0. There is a finite value, right? Light is traveling from a rarer to denser medium, so it should bend rarer to denser towards the normal. So at the second interface, light is traveling from a denser to rarer medium, so it should bend away from the normal. So the net result is light bends towards the optic axis. This is called the optic axis. It hits this point here, which is the focal point. Now let's move a little bit further up. What would you expect with respect to the angle of incidence? Much higher. So angle of refraction is higher as well, and the same thing happens at the second interface. You have much more bending of light at a point that is above this. So what is this gradient giving you in the convex shape? It's giving you an ability to progressively increase the angle of incidence so as to progressively increase the bending of light with the ultimate aim of bringing all the light to one point, which is the focal point. So what we need to remember here is there are two interfaces. Interface 1, light travels from a rarer to denser medium and light bends towards the normal. Interface 2, light travels from a denser to rarer, bends away from the normal, but in both cases it is bending towards the optic axis, just because of how the geometry is. In both cases you see light is bending towards the optic axis. Alright, now this is something that we have all drawn in your high school, right? How many of you have drawn these diagrams? Okay, good, very nice. That means I don't have to spend a lot of time here. But what are we really trying to do here? We have chosen an object, right? What is the object here? It's an arrow. Do you know why we choose an arrow? Yeah, it has a sense of direction, yeah? And it's a very simple object. It's a simple object would have been a line as an object, but then line does not give you a sense of direction, so we choose an arrow. That's as simple as it gets. Now if you want to really do it perfectly in an absolute world, you see that this object, how many points are there on this object? Infinite number of points, right? And on each of the infinite number of points, if you send light at least in a theoretical world, you will have infinite number of scattered rays. You should have considered all these rays and traced the ray diagram. But that is complicated, so we are going to highly simplify this. I am going to take only one point here, the tip of the arrow, yeah? And from the tip of the arrow there is ideally infinite number of scattered rays, but I am selecting only two. One scattered ray that goes parallel to the lens, and what happens to that light? It doesn't matter where it comes from. If the light is parallel to the optic axis, it will pass through the focal point. And another ray that passes through the center will go through undeviated. And the place where they meet is the focal point, and that is where you create the image of the tip of the arrow. If I know where the tip of the arrow is, I can extrapolate it to the optic axis, and that will give me the base. So this is you cannot make this ray tracing problem simpler. Now, you know what 2f and everything else, so I'm not going to explain that. So let's assume I am the arrow, right? So I am the arrow. Where am I standing now? I'm standing at infinity, and light is falling on me, and it's getting scattered. Where is my image formed? Image is formed at the focal point because I'm standing at infinity. Now I'm walking a little bit forward. I reach somewhere between infinity and 2f. Where is my image formed now? It is formed between f and 2f. Yeah, what more can you say about the image? It is inverted. What more? Is it magnified? Is it magnified? It is smaller. It is demagnified. So if I'm building a microscope, yeah, this situation is probably not very encouraging for me, right? So I'm standing between infinity and 2f. Now I take a step closer and I'm now at 2f. Now this is a very interesting situation, right? When I'm at 2f, my image is formed exactly at 2f on the other side. What about the magnification? The same. Now, if you're designing optical system, this kind of system is called a relay system, because whatever is my size, it's exactly relayed onto the other side. So, if you're building something called a relay lens, you can make use of this. So, if you're taking the microscopy project, we will build a relay lens to image the back focal plane of the microscope. Okay, now I'm at 2f, I'm moving a little bit more forward. What happens? I'm standing somewhere between 2f and f. My image is formed between 2f and infinity. And what else can you say about it? It's magnified, it is inverted. Inverted is usually not a big problem. Let's say I'm looking at a cell, right? So it doesn't matter whether I am looking at it this way or that way. I want to look at the details. So being inverted is typically not a problem for many applications. There are some cases where you should be aware of it, but if you know that it is inverted, you can always account for that. So now this is an interesting situation for us because we are interested in making microscopes. So one of the situations that you can use here is when the object is placed between 2f and f. Now I keep walking towards f. I'm still between 2f and f. I'm walking towards f. What happens? This image gets further and further away from 2f, right? And what happens to the magnification? It increases. So as I move from 2f to f, my magnification keeps increasing until I reach f. What happens at f? Magnification is infinity, right? And if I still keep walking further, I don't have the light converging at any point, it is diverging, but I create a virtual image. Now this description of optics with light rays using the concepts in geometry and trigonometry is called geometric optics. Now geometric optics is a very old field in the sense that people have been studying this for, I don't know, more than 1,500 years now. The first books in geometrical optics were written more than 1,000 years ago. And in which language are they written? It's in Arabic. Yeah? So it's not surprising because if you look at history, that period, the Middle East is the hub of trade, commerce, science, art, mathematics and so on. You might have heard of poets like Omar Khayyam or the mathematician Al-Khwarizmi. So algorithm, algebra, it's all, the name comes from Al-Khwarizmi. So there are a lot of mathematicians and scientists in the Middle East during that time. And one of the scientists was Ibn Shal. So Ibn Shal was a mathematician, physicist and optics engineer in the court of Baghdad. He was probably an advisor to the king on matters of physics, optics and mathematics. And he wrote this book called the Book of Burning Mirrors and Glasses. What is a burning mirror? What Archimedes were trying to do, right? If you take a concave mirror, you can focus sunlight and burn. And if you take a convex lens, you can focus sunlight and burn. So in those days, convex lenses and concave mirrors were called burning mirrors and glasses. That's how they were described. And his book is called Kitab al-Harakat. Now you look at this diagram here. What he's trying to do is to describe or trying to study a lens as part of a sphere. But even more interesting is this diagram here, which might look a bit complicated, but what he has tried to do is to study refraction. So this is your incident ray, right? This is your refracted ray. And if you extrapolate this, you get this diagram. And now, you know the law of similar triangles, right? By law of similar triangles, you have two triangles here. BDO and BAO, and from that it turns out sin theta 1 by sin theta 2 is BD by AB, which is nothing but the Snell's law. So Ebenthal probably did not understand that this ratio is equal to the refractive index ratio of the media, but he knew that this law exists. And it's very likely that it was Ebenthal who first discovered the law of refraction, at least in a limited way. Snell was probably able to attribute that ratio to the ratio of refractive indices. Now, one of the even more important books in that period was written by Hassan bin Haytham, who was born in Basra. You know where Basra is? Basra is in Iraq, a city that still exists, like Baghdad. So Baghdad was probably the intellectual capital of the world during that time, and cities around them were significantly contributing to that. And what happened is, Ibn al-Haytham, he collected the works of several of the previous scientists during that time, including Ibn Shal. He added his own work to it, and then he wrote a treatise with 7 volumes. So this is quite an elaborate book with 7 volumes, and he describes the theories of light, color, reflection, refraction, and even vision. So his idea of vision is kind of similar to what our current idea of vision is. What happened then is, about 200 years later, because Arabs were trading with Europe, this book get translated into Latin, and in Europe, Al-Hasan was called Al-Hasan, and this is a book of optics by Al-Hasan. And this book is considered one of the most influential books in optics ever written because of what it triggered in Europe in terms of research and understanding of optics. So this book extensively affected the development of optics in Europe in the 13th to 17th century. And you can imagine that's when Snell came out with the Snell's law, and probably it's very likely that he had access to information from this book. Alright, so now we know about lenses a little bit. What is the next thing we need to do? We need to put the lenses together and create an optical system, an imaging system. That means we need to know what is imaging. So what is imaging? Put it very simply, you have an object and you want to capture an image of the object on a screen, and that is imaging. I have an object, I want to capture an image of the object on the screen. How do I do that? I send some probes, some particles. What kind of particles can I send to this object? I can send photons, which is the most commonly used particle for imaging, but I can also send other particles. I can send electrons, I can send ions, I can also send X-rays. X-rays are also photons, but yeah, X-ray microscopy is a different thing. Okay, so if I simply send light to this object, or let's say photons to this object, and the light gets scattered, and I collect the scattered light on a screen, will it create an image? So have you tried this? Take a flashlight, illuminate an object, put a screen in front of it. Will you see an image? You will not see an image. You will see a smear of intensity on that screen, but you will not see an image. Why? The reason is, if I take a point on the screen, right, this point gets light from almost every point on the object. So it gets light from point A, point B, point C, and pretty much every point on the object. So there is nothing unique about the light falling on the screen. It receives, every point on the screen receives light from multiple points on the object. So one way to create an imaging system is to put a pinhole. What is a pinhole? It is a metal block or a metal sheet with a tiny hole in it. Now if you take a look at this, the light that is falling on the point A dash on the screen is predominantly coming from point A. Light falling on point B dash is predominantly coming from point B, and the light falling on the point C dash is predominantly coming from point C. So simply by putting a pinhole in front of your object, you can create an imaging system, and this is the simplest imaging system that you can build. And such an imaging system is called a pinhole camera or a camera obscura. So this is an idea that was used in practical cameras. So when I was in my primary school, long time ago, maybe not so long ago, if you went to a photographic studio, an indoor studio to take passport size photos, they would typically use a pinhole camera. And the images were quite nice, very, very, very nice. So I don't think any of you have ever taken your photo using a pinhole camera. Has anybody done that? Anybody in the audience taken a photo of yourself using a pinhole camera? Huh? Yeah, okay. But you did not put a film there and produce it, right? Okay. So it's believed that the first pinhole camera was built by Al Hassan in Basra. So what would he do? So in fact, this is a very nice experience if you can build it in a room. So he would close the window, put a little hole, and then on a very sunny, bright sunny day, which is typically the case in those places, the minarets of the palace could be projected on a screen. And this looks extremely nice because you have a giant screen on which this image is projected. So you would amuse the citizens of Basra with this illumination method. So a lot of science would get done in these places, in Baghdad and Basra during those days. Unfortunately, I think right now, the amount of science happening in Iraq is a tiny fraction of what happened 1,500 years ago. I hope that changes sometime soon. Okay, so now there is a fundamental problem. So this is the simplest imaging system, very easy to fabricate, hardly any, there is just one part that you need, but there is a fundamental problem with this. The problem is you are blocking a lot of light, and the smaller you make the pinhole, sharper the images, but then the light gets dimmer and dimmer. So this is not a very efficient imaging system. So what we need to do is replace the pinhole with something like a collector. So what does this collector do? I'm using this general term called collector. This collector should collect all the light from point A and project it to a unique point A dash, collect all the light from point B and project it to a unique point B dash, and similarly from point C and project it to a unique point C dash. This should do it for all the points on the object. And if you do that, then you have an image. So we can say that what the collector does is it maps the probes from a point on the object to a unique point on the screen. So what is imaging then? Imaging is a process of mapping. You map the points of the object to a point on the screen using the probes and the collector. Now if your probes are photons and your collector device is a lens, then we call it a optical imaging system. So the first optical imaging systems were probably eyeglasses historically, and this Italian, I don't know if he was a scientist or maybe he had a workshop to build lenses. So Salvino de Armate is credited with building the first eyeglasses. And people who built eyeglasses later started putting these lenses together to experiment with them and started building microscopes. So the simplest, let's say, microscopy system, we cannot really call it a microscope, it's a magnifying glass, right? How does a magnifying glass work? You have a magnifying lens, and now you have to put the object somewhere. Where will you put that object? There are different places in which you can put the object. You can put it between, at infinity, between. Yeah, you put the object at a distance shorter than the focal length. Then what happens? You are not converging the light, but you are diverging the light, right? And then if you look at this with your eye, and if you trace the light, you see you have a magnified image on the same side of the object, and it is upright. Now the question is, are you creating a real image or a virtual image? Is there anybody who thinks you are creating a real image? Anybody in the audience? No one? You are creating a real image. Now to explain that, I have to ask another question. How many lenses are there in the system? 2 lenses. The magnifying glass and the eye, right? The magnifying glass produces a virtual image, but the eye produces a real image on your retina. Because the eye produces a real image on your retina, that's why you are able to see it. right? So a magnifying glass by definition is not a microscope, even though it is magnifying. So what is microscopy? It comes from this Greek words micros and scorpion. Micros means small and scorpion means to observe. And the simplest microscope you can build, we have already seen how to build that, right? How do you build that? You keep the object between f and 2f, right? When you do that, you create an image between 2f and infinity on the other side. Now, if you have a magnifying system, you also need to know what the magnification of the system is. So for that, let's look at the two triangles here. So what is magnification? Magnification is the ratio of your image, size of the image divided by size of the object, right? And if you look at the two triangles which are similar triangles, this ratio h dash by h is equal to b by a, which is nothing but distance of the image from the lens divided by distance of the object from the lens. Is that okay? Alright. Now, if I want to capture an image, I can put a camera here, a camera sensor, which works fine. So yesterday, people who came to the microscopy project, the introduction session, you saw the camera, and the camera did not have any lens. It was just the bare sensor. So if you keep the bare sensor of the camera here, you can create an image. Now the problem comes when you have to look at this image using your eye. What is the problem? You are introducing another lens, which means now I have to introduce an additional lens called the eyepiece. The eyepiece, let's assume it has a focal length of FE. It has to sit exactly at its focal distance from this point, right? So you have a point here. This is a focal distance. What will happen to the light coming out? It should be parallel, right? And then the eye can create an image on the retina. So the whole reason why we are introducing the eyepiece in a system, and the name is quite explanatory, is because you want to create an image on the retina. Now the problem here is you have the space between the objective lens and the eyepiece, which is called the tube length. So if you look at older microscopes, you have a tube into which these two lenses are fitted, and this distance is fixed. You cannot change that once you have fixed the magnification of the system. Now this creates some problems. That's why newer or latest microscopes don't use that design. So the earlier design is called the finite tube length microscope. You have a question?
Yes. So in the previous diagram, so the object is placed between the f0 and the 2f0 area.
Yeah.
What if it is placed beyond 2f0?
Oh, but what if you place it beyond 2f0? Yeah, but then you don't have magnification. We saw the diagram earlier, right? So that is simple. Look at this image. We started by placing it beyond 2f, right? And look at the image, it's not magnified. So you cannot use this arrangement to create a magnifying system. You have to use this arrangement to create a magnifying system.
What if we need a diminished image?
Yeah, then you can, but then it's not a microscope, right? The whole idea of microscope is it magnifies. There are systems where you want to diminish, but then, so then you can look at it as a telescopic system, a photographic camera, for example. It's not a microscope, it's a telescope, right? Because if you have a tree, you create an image of the tree which is much smaller, right? Okay, so let's go back. So the finite tube length design has some problems. For example, the tube length is limited. So the modern microscopes use what is called as a infinite tube length design. So what happens here is you keep the object exactly at the focal point. So what will happen then? There is no image formed. Light comes out parallel. So what should you do now? Put another lens. So this lens would then focus the image, create an image at its focal point, and that can be magnified under certain conditions. Yeah, So we need to know what those conditions are. So that's why let's look at the magnification of the system. And by the way, because the light is coming in parallel between the objective lens and the tube lens, you can put these two at any distance. So if you are a microscope manufacturer, the space between the objective lens and the tube lens can be used for other things. Put in polarizers, put in filters, put in partially reflecting mirrors. There are a lot of other things that you want to put. So from an engineering point of view, this is a much better design, simply because you have more space. Now we said the magnification of the system is the distance of the image from the lens divided by distance of the object from the lens, right? So what is the distance of the image from the lens, which is, this is equal to the focal length of the tube lens, and distance of the object from the lens is focal length of the objective lens. So what is your magnification? It is nothing but focal length of tube lens divided by focal length of the objective. So this actually means that to have a higher magnification, you need to use a tube lens of longer focal length. A shorter focal length for the objective lens and a longer focal length for the tube lens. Is that okay? Alright? Now, again, if you want to create an image, you can place the detector or the sensor of the camera here. But if you have to observe it through your eye, you have to introduce the eyepiece again. So how many lenses are there in the system? 4 lenses. Objective lens, tube lens, eyepiece and the eye. So this is a 4 lens system. Now when you look at objectives, I don't know if you have seen microscope objectives, they all come with this number that says magnification. For example, this is a ZEISS apochromat objective. It says the magnification is 63x. But we said magnification depends not just on the objective but also on the tube lens, right? So why did this or our company put a number to this lens here? So this actually means that the magnification of 63x, you only get it when you match it with a specific tube lens. So this objective is designed for a specific microscope with a specific tube lens. If you take this objective and put it in on, let's say, Nikon microscope, you may not get the same magnification. Also, there are some aberration correction of that you need to keep in mind. So every objective is designed for a specific tube lens, and usually companies will not tell you what that is, what the focal length of the tube lens is. That is for some reason kept a secret unless you specifically ask for it. Okay, now there are something called aberration. So this is a big problem in microscopy. You want to create a sharp image, but your images are not always sharp. You might have seen this with magnifying glasses, right? Have you tried observing something with a magnifying glass? The edges of it would look little bit blurred, right? So that is called spherical aberration. And similarly, you might have chromatic aberration because different wavelengths of light have slightly different refractive indices, because of which you have different focal lengths. So like a magnifying glass, if you have a magnifying glass with a large diameter, you see that the aberrations are more pronounced, right? But we also talked about numerical aperture. Larger the diameter of the lens, more is the light collecting capability of the lens. So you have now two things that are little bit working against each other. A larger lens is required for a higher numerical aperture, but you need a smaller diameter to reduce aberrations. So what typically is done is, you have objective lenses that are designed with a small diameter but with a large curvature. So you can design let's say a system or a lens which has a large curvature but a small diameter. So that will give a high numerical aperture because it can collect light at a very high angle, but it will have smaller aberrations. Now one person who really exploited this idea, and in fact in my opinion built one of the best microscopes in the world, is Leeuwenhoek. And his microscope is, the size of his microscope is half of a credit card. You know the size of a credit card, right? It's half of that. So this is a little piece of metal with a tiny hole in it. Yeah, and what he would do is he will melt glass, and through a small tube he will drop or create a small drop of glass, and because of surface tension it will become a sphere. and sphere has a very high curvature, right? Now he had to do a lot of trial and errors. If you adjust or get the distance right, when the drop reaches that hole, it is cold enough to maintain its shape, but soft enough to get stuck in that hole. So that's how he created this so-called high-performance microscope, which is a plate with just one lens. Now, what he also did was to put the sample in this little pin, and there is a very precise arrangement to move it in X and Z directions. So with this microscope, he could have a magnification about 250x, rather high numerical aperture, very low aberrations, and he could get some extremely clear images. What is even more interesting is with this apparatus, if you know the pitch of the screw, right, because you can move it very precisely, it could, if you see two objects, you can kind of measure how many rotations it took for this object to move from this end to that end. By that, he could have even made measurements of the size of the object, and that is quite remarkable what this microscope can do. Now, I think personally, if there is a prize for the microscope with the best performance to complexity ratio, this microscope would still win that prize, even with all the $1 million microscopes that is around in this world. And of course, he took some nice images and were able to detail this. Now, if you look at modern microscope, they also use the same concept. They have borrowed the idea from Leeuwenhoek. So this is how a microscope objective looks like. They have multiple lenses. Why do they have multiple lenses? So all to correct aberrations. So each lens has a different refractive index, different curvature. They're all put together. So a expensive lens. So this lens, which is called apochromat objective, can have, it can cost as much as 3,000 euros. Yeah, so it can cost you as much as a car. And there are about 25 to 30 lens elements with different refractive indices, different curvatures, all aligned to make sure the aberrations are reduced. But the most important thing here to notice is the front lens. Did you notice the front lens? This is the most important lens in the objective. What is it? It's exactly a sphere of glass. Very similar to what Leeuwenhoek used, but instead of a sphere, we use a hemisphere, because if it is a sphere, it will project out of the objective. You need a flat surface, so you have used a hemisphere of glass. So same idea that Leeuwenhoek used is still used in modern objectives. Now these are some of the older microscopes, earlier microscopes, and what is the first thing you notice here? What is the most, if you were to ask, describe this, what is the first thing that comes to your mind? These are pieces of art, right? They're not, this is not how modern microscopes look like. It's a lot of effort, more effort has gone into make it an artistic product.
I think we don't have like any objects to make finer adjustment, or like no light sources we can have to.
Yeah, so you don't really need it. So in those days, you would use natural light as a light source. Yeah. But the reason, there are few reasons why these are made like artistic products, but one of the reasons is who were the customers for microscopes? They were not scientists. There were not so many scientists using microscopes. There were also not industries who wanted microscope to do precise measurements. A lot of the microscopes were purchased by rich people, aristocrats, who would buy this and put some pond water under it and amuse their guests. So this was a tool for amusement, like the what is a kaleidoscope, right? That you can play with. So microscope was like kaleidoscope, which was a tool for amusement. But one of the first people to use microscope for a scientific study, proper scientific study, was Robert Hooke. You know about Robert Hooke, right? Yeah. So if you are in biology, is like the father of cell biology. But if you are into material science, Robert Hooke gave us the Hooke's law. I don't know if you know about Hooke's law that relates stress to strain. Yeah. So that is a very fundamental relationship in material science. So if you are constructing a bridge, you might, of course, you might want to know about the Hooke's law. Now let's take a closer look at this microscope. This is a very elegantly designed microscope. Yeah. So the light source, there are no electrical light systems. You have a lamp, oil lamp, and this is where the flame is produced. And this light is collected by a collector lens, which is essentially a flask filled with water. Remember the bottle filled with water? The same idea here. You have a sphere of glass filled with water that gives you a very high numerical aperture. So you can collect a lot of light from the lamp. and there is a condenser lens that condenses the light onto the sample. The objective is placed in this little tube, which means the tube diameter is small. So the diameter of the lens is small, which probably means it is a high curvature, small diameter lens. Not as small as what Leeuwenhoek used, but still small diameter, high curvature to make sure aberrations are reduced, but you still have a high numerical aperture. This is a finite tube length design, which means the object is placed between F and to F, but most likely closer to F, because as you get closer to F, the image is formed a long distance away, which means you have a high magnification. So this system is very nicely designed. It has high magnification, high numerical aperture, low aberration, and a very elegantly designed illumination system. So a lot of thought had gone into the design of this microscope. These are some of the images in micrographia. You can imagine in those days there were probably no photographs, cameras. So the person had to look through the microscope and draw these pictures by hand using something like a pencil. So enormous amount of effort and time has gone in to make this microscope. Sorry, these images. Okay, now we are coming to almost the last part of this story that I want to tell, the history of microscopy, right? And we have traveled to a few different places. We started with Greece, we went to Philippines, Basra. What Robert Hooke did was probably in the UK, and the last stop is Germany. City of Vienna. And this is a time when industrial revolution was, it was accelerating. And because of this, there was a lot of demand for microscopes, because industrial production means you have raw materials that needs to be inspected. The final finished good needs to be inspected to see if they are within the tolerances, if the mechanical measurements are all correct. So this created a lot of demand for microscopes, and it is said at that point of time there were like 200 companies in Germany making microscopes. And these are not really companies in the company sense, they are basically workshops, mostly eyeglass manufacturers who started doing trial and error. They'll put two lenses together, create a microscope. So now what happens is, if a company then orders 3 microscopes exactly same, the performance is not the same because it is built using trial and error. The quality of the microscopes were also really bad. So one man decided that this has to change. We need a proper scientific way to design microscopes. You have to first theoretically design the microscope and then convert that design into a product, so that there is reproducibility and there is the quality of the microscope is also high. So this person is Ernst Abbe. He was a professor of experimental physics at the University of Vienna. He was the research director and co-owner of Carl Zeiss, the company that I work for now. This is actually a 200-year-plus old company. So Carl Zeiss started the company, but it was Ernst Abbe who really made the advances in the company. And he made this company into a foundation. So it's still a foundation. So what Ernst Abbe did is, he applied physics and mathematics to design microscopes. This was the first time microscopes were properly designed. So nowadays, if you have to make any product, first you design it on a drawing board, or nowadays in computers, right? So he applied physics and mathematics to design microscopes. He introduces scientific principles in manufacturing and assembly of microscopes. He introduced some labor reforms. And he also realized that if you want to make a good quality product, you also need a good quality testing process. For that you need to do precise measurements like measuring the focal length, refraction of materials and so on. So he invented the focometer, refractometer. He invented the microscope test slide where you can measure the resolution of the microscope. He defined the idea of numerical aperture. So the numerical aperture that I was talking about, he conceptualized it. He designed the apochromatic objective, and what he's really famous for is the Abbe's resolution limit, and we will talk about that in a moment. But one of the unsung heroes of microscopy is Otto Schott. So when Abbe was designing his microscopes, especially the apochromatic objective, he realized that he needs glass with very different refractive indices, which was not available during that time. So what he did was he used oils of different refractive indices. He made a lens that works, but you cannot use it practically. It was just a proof of concept. So when Otto Schott started working with Abbe, he formulated, or he was a chemist, a glass chemist. He formulated the glass formulations, and then Abbe was able to make his apochromatic objectives. And Schott started a company called Schott, which still exists, and Schott and Carl Zeiss are both part of the Carl Zeiss Foundation. Now this is one of the first microscopes designed using scientific methods and then mass produced. Now the last topic I want to discuss is resolution. Do you know what resolution is? Resolution is the ability for two objects to be separately seen, to be seen distinctly under a microscope. So I have two images here with the same magnification, but which image is better? This one, right? Because even though they have the same magnification, you can see more details in this image. So this means this image is more resolved than that. Oh, that is probably something floating, because this is under a liquid. So this is a, I think a diatom. Diatom lives in water, so you typically collect it from a pond, and you still have some water medium. So maybe there was something floating when we took this image. Yeah, but good observation. So Abbe came out with this idea that resolution of a microscope is proportional to the wavelength and inversely proportional to the numerical aperture. Now the question is, why is resolution depending on wavelength and numerical aperture? Because when he introduced this was a very radical idea. To understand that, we need to understand what is called as wave optics. So everything that we learned so far was ray optics. We are using geometry and trigonometry to study how light propagates through optical elements. But to explain resolution, you need to understand that light is a wave. What kind of wave is a light wave? It's a transverse electromagnetic wave, which means you have a varying electric field that creates a varying magnetic field, and the varying magnetic field creates a varying electric field, and then they sustain each other. So that's why light can even propagate in vacuum. You don't need a medium, because these two are sustaining each other. The electric field, let's say, is in the x-axis, the magnetic field will be in the y-axis, and the light itself propagates perpendicular to both these electric and magnetic fields. And it was Maxwell, James Clerk Maxwell, who put this into a mathematical formulation, and this is the famous Maxwell's equation. So if you learn physics at the graduate level, then you will learn about Maxwell's equations. So Maxwell's equations have a huge impact on our lives. 5G, satellite communication, optical fibers are all possible because of Maxwell's equations. But we don't have to look at Maxwell's equation, because light as a wave is complicated. We can look at something simpler. What is a simpler wave that is transverse in nature?
The next thing I want to look at is what happens to
Is a water wave, right? A wave in water. So
a water wave when it passes
let's
through
look
an
at how
aperture.
water waves
Well,
behave.
I fitted an aperture here, but it's rather too wide for what I need at the moment. So if I fit these sliding doors, I can make an aperture that's about 3 centimeters across. And if you now look at the screen, you can see that as the waves pass through the aperture, they spread out. This spreading out of a wave as it passes through an aperture is known as diffraction, and it's a property of all types of waves. So what do you think controls how much the wave spreads out? Well, one possibility is the width of the aperture. And what do you think would happen if I made the aperture smaller? I can make an aperture that's about 3 centimeters across. And if you now look at the screen, you can see that as the waves pass through the aperture, they spread out. This spreading out of a wave as it passes through an aperture is known as diffraction, and it's a property of all types of waves. So what do you think controls how much the wave spreads out? Well, one possibility is the width of the aperture. And what do you think would happen if I made the aperture smaller? Well, you might be surprised to learn that a narrower aperture leads to more spreading out of the wave, more diffraction. If instead I make the aperture wider, then after it's settled down, you can see that the wave becomes less spread out. The diffraction is less pronounced. And if I were to make the aperture very wide indeed, then there'd be hardly any diffraction. Well, I'm now going to return the aperture to its original width and take a look at the effect of changing the wavelength of the wave. Now remember, I can change the wavelength by altering the frequency of the paddle using this control here. If I make the wavelength longer, you can see that the waves become more spread out beyond the aperture, more diffraction. And if I make the wavelength smaller again, here's where we started, then even shorter wavelength, then there's less diffraction. So here are the two separate factors that affect the diffraction of a wave passing through an aperture. The wave spreads out more if the aperture is made narrower or if the wavelength of the wave is increased. And conversely, it spreads out less with a wider aperture or a shorter wavelength. In fact, all kinds of waves, not just water waves, exhibit diffraction at an aperture, as long as the aperture is not too big.
Okay, so what did we learn here? If you have a wider aperture, you have very little diffraction, right? And if you have a smaller aperture, you have more diffraction. So what if you have a plate with two little holes, both of which can produce a diffracted pattern? Then what happens? Then these two diffracted patterns will interfere with each other to create this diffracted orders of light. So you create a fringe pattern which is interference of diffracted waves, and that causes maxima.
Two sources of ripples, which are basically like the two slits. When I create ripples with a single source, they travel out with circular wavefronts. Nothing particularly surprising there. But if I add a second source of ripples, then we start getting an interesting pattern. This pattern is created by the ripples from the two sources interacting with each other. Where they meet up peaks with peaks and troughs with troughs, the amplitude of the wave is increased. That's what we call constructive interference. But if the peak from one wave meets up with the trough from the other, then we get destructive interference, and there's basically no wave there. And this is exactly what was happening with the light.
So you have these two sources of light from the two slits. They create diffraction pattern and they interfere with each other to create these diffracted orders of light. Now let's assume we have this double slit. Here the slits are separated. There is a certain distance between them. And what happens to diffracted orders? They are closer to each other. What happens when you bring the slits closer together? Diffraction will increase, right? So the angle between the zeroth order and the first order will increase. So you have a wider separation between the zeroth order and the first order. So for a smaller gap between the emitters, the interference order span a larger cone. Now let's assume you have the two slits, two double slits with the same separation, and to one you impinge blue light. Blue light has a shorter wavelength, which means you have a smaller separation between the diffracted orders. What if you use red light? More diffraction, which means there is more separation between the diffracted orders. Now, this can be observed in the back focal plane of a microscope. The zeroth order is always in the same place. So if you look at the zeroth order and you are using white light, you will see the zeroth order is white. Whereas if you look at the first order, the blue light has a smaller separation and the red light has a larger separation. So the light wavelengths get spread out in space when you look at the higher order diffracted light. Now this has a consequence in when you look at resolution of a microscope. Now I have this slits, a double slit, and I cannot see it with my naked eye. So I place it under a microscope, and my microscope is a infinite tube length microscope, which means my objective is sitting at its focal length away from the sample. The objective is now collecting the 0th order and some of the higher orders. The objective will then, what will it do? It is sitting at the focal length of the sample. Light will be collimated out of the objective. You have the tube lens which will then focus the light and create an image. So what exactly is an image? Image is created because of the interference produced by the tube lens between the 0th order and the higher orders. So image is nothing but an interference pattern. It is formed by the interference of diffracted and undiffracted light, which means to create an image you should be able to collect not just the 0th order but also the higher diffracted orders. Now let me bring the separation between these two slits closer together. Now what happens? The slits are closer together, diffraction is more, the angle between the 0th and first order is larger. This means this objective, particular objective with a certain numerical aperture is unable to collect the higher order diffracted light. It is collecting the 0th order, but it is not collecting any of the higher ordered light. That means the tube lens, even though it has light, it is collecting light, it is not creating any image. And this is why numerical aperture is so important for microscopy. If this objective had a higher numerical aperture, it would have probably collected the first order diffracted light. So what does this mean? This means the idea of numerical aperture. So numerical aperture is n times sine alpha. Alpha is the half angle of the cone of the light subtended by the lens here, and that becomes quite important for resolution. So I have three lenses here, one with a 7-degree half angle, another with 20-degree half angle, and the third one with a 60-degree half angle. Which one will resolve better? One with the higher numerical aperture, because if you have two objects that are closer together and if it produces a diffraction pattern that are separated out, this objective can still collect it. So this idea, this is pretty much my last slide. So this idea was described by Ernst Abbe in 1873 in this paper that he published, which is called The Theory of Microscope and Microscope Imaging. And here he clearly describes how diffraction pattern is formed on the back focal plane of the objective. He used a test slide. You remember the test slide that Abbe designed. So in this test slide you probably cannot see it clearly here. So here you have lines or grating lines that are closer together, and here you have lines that are more separated out, and you can clearly see that the diffracted patterns are closer here and separated out. When the lines gets closer, diffracted pattern gets more separated. So there is an inverse relationship between separation of objects and separation of the diffracted orders of light. Okay, so this is a great idea seminar, right? So what is a great idea that you got from this seminar today? In fact, I think there are a lot of great ideas, right? Archimedes' idea of putting the mirrors together to create a concave mirror, that was a great idea. The bottle filled with water, that was a great idea, right? Putting a little pinhole in front of object to create an image, that's also a great idea. But probably the greatest of all, at least for me, I mean, each of you could choose your own, is this. The idea that resolution depends on the wavelength and numerical aperture. And so this was published in 1873, and since then there have been people trying to see whether you can overcome this. Till now nobody has really been able to overcome or break the diffraction limit, but there were 3 scientists who managed to work around this, and to create high resolution images. So there is a fundamental resolution limit, which means for a given wavelength and numerical aperture, there is a certain resolution, and you cannot break that resolution limit. You can work around it, but you cannot really break this. With this, I want to, yeah, you have a question?
Okay, so if you read class 10 NCERT, like you have to start with light, reflection, and refraction, I believe. So, like in that chapter, they okay. Yeah, so the spherical mirrors that they are referring to in that chapter, they say that the aperture is smaller than the focal length. Like those are the spherical mirrors that we are considering. But then, if the aperture is the diameter of the sphere and the
So aperture is not exactly the diameter of the mirror, right? So aperture is the angle that it subtends. So for example, that's what I was trying to say. You can have a smaller diameter but a larger curvature. So it depends on both the factors. So you can have a higher so that's why this aperture is called a numerical aperture, not the physical aperture. So you can have a larger aperture with a larger diameter or a smaller diameter with a larger curvature, which means it then subtends a larger angle. So this angle that, so if you consider the focal point, from the focal point, what is the angle it subtends? That is what is important here.
Excuse me, just start with your name and from the place where you belong so that it would be easy for him to address you.
Yeah, so if you assume you have a light wave, right? So assume the wave is like this, right? So if you have two wavefronts that come one after the other, so this is called constructive interference. But imagine so wave looks like this. What if I slide the wave to this side, then this part of the wave comes. So one is like positive, other one is negative. One is trying to move up, other one is trying to move down. And if these two come together, then they collapse. So there is no wave there, right? So which means for water waves, it means that part should be still. There should not be any movement. But for light, that means it is dark at that point, where you have destructive interference. And where you have constructive interference, it is bright. Is that okay?
Hello, sir. I'm Mannat. I'm from Delhi, DPS Arkepuram. So, in your talk, you mentioned that we should have a larger lens to have a larger aperture and a smaller lens to have smaller aberration. And you also said how a few scientists had made it possible to have a larger aperture and minimized the aberrations too. So, what are the additions or what are the changes that are made to a microscope typically to have a larger aperture and to not compromise the aberrations?
Yeah, so as I was showing you in that image, so modern microscopes have newer tricks to solve the aberration problem. So if you look at the image that I showed here, so in the earlier days, you had just one lens for the objective. So you had to, whatever you had to do, you had to make with that one lens. So whatever you could try, you had to try by minimizing aberration for that one lens. But modern objectives have the liberty of using multiple lenses. So let's assume, so you start with the basic concept, right? You start with a lens with a large curvature, small diameter. This is your front lens. So that pretty much minimizes the aberrations, but it's still not gone. And then you have multiple lens systems. Some of them have different refractive indices. Some of them have something called the negative refraction, all those to correct for chromatic aberration. And then there are lenses with a positive meniscus and a negative meniscus. So this optics design is a bit complex, but the idea of having all these lenses together is to make sure that together they act as one lens, but these lenses would minimize aberrations. So there are spherical aberrations, there are things called astigmatism, so there are several kinds of aberrations that are corrected here. Did I answer your question? Go on, that's the question.
Good afternoon, sir. I am Earth from Delhi. I wanted to ask, which is the object that has that is ideal for making a lens, a sphere or some other object having a higher numerical aperture and a smaller diameter?
Oh, you mean the shape or?
The shape.
Yeah. So this biconvex shape is the one that is most commonly used. Yeah. But that is not the perfect shape for a lens. There are lenses called aspheric lenses. Yeah. Because what happens is, as you saw, when you move from the center to the periphery, the bending increases, right? With the ultimate aim of bringing everything to one point. But this increases a little bit more than what you need. Yeah. So you have lenses where it's biconvex but little bit more flattened out on the periphery. But the problem is it's very difficult to design those lenses. Lens making is still an art. So the people who make lenses are not called technicians, they are called artists. Because they polish the lenses by hand. And this is a trade secret that, there are 4 main companies, right? Carl Zeiss, Nikon, Leica and Olympus. They're the 4 main manufacturers of lenses and they keep this as a trade secret. So for the very high numerical aperture objective, a person has to manually polish the lenses. And you can only do it with a biconvex lens. So even though biconvex or convex lenses are not the best shape, we still use them because we know how to correct for aberrations by putting additional lenses in the system.
Thank you, sir. I wanted to ask the second thing. Like in the beginning, you were talking about the photons as props. So does this account for the wave nature of light, or does this only talk about the particle nature?
Yeah, so as far as microscopy is concerned, we are more concerned with the wave nature of light. So I told them as probes because I wanted to talk about the different types of particles you can use. You can use electrons, you can use ions, you can use photons. But in all of them, what is the best? Because light has both particle and wave nature. Electrons also have particle and wave nature. But now the question is, what nature of that particle is best to describe what you are trying to study, right? In our case, for imaging, it's the wave nature that will be more suited to describe it. But like yesterday, I think we talked about the photoelectric effect, right? So there you really need to look at light as a particle, but you don't need to really use that you need, the camera is a photo detector, but to describe imaging, you probably don't need to look at light as a particle. No, I think that for any topic, right, even the topics that people thought are completely dead, you realize that there is something more to discover. So for me, personally, I would say there is no topic that is dead. For in every topic, there will be something to discover. To answer specifically your question, there are a lot of universities that have programs called biophotonics or, there are life science departments that have a strong microscopy program. So they are building new types of microscopes. Because if you look at most of the microscopy advancements, they are not coming from companies, they are coming from universities. So this super resolution microscope, let's say one of it's called a STED microscope. It was, I forgot, from a university in Germany. Another one was from Harvard University. So universities are still actively involved in expanding or the technology of microscopy, and what companies like us we do is to go and get the technology from them and then convert them into useful products. Not to say that innovation is not happening, but from a techniques point of view, a lot of innovation is happening. So if you want microscopy to be your scientific field of research, there are enormous amount of opportunities.
I would like to just expand on what she asked. So there are many books which deal with this question, like is the research in science dead because the great revolution of science was done in 19th century and it began with Newton and all. then Einstein added to its to great extent, and on the other side, Darwin added to the biological discipline. So there's a very good book called The End of Sciences. It's by John Hogan, if I'm not wrong. He's an American journalist. So it actually deals with the very basic question that if the science dead today, because because all the things which were important we have already discovered. Is there something which is left to be discovered in future or not? So there's a whole book which deals with this. So maybe you can read if you want.
Yeah, obviously. So science has become multidisciplinary, and if you look at the most impactful research that is happening, it's happening as a collaboration with several universities. Especially in yesterday's talk, you saw that discovery of the LIGO program. I mean, there were like 40 authors or 50 authors, and I don't know how many, 20 institutions. So that's the level of collaboration you need for modern or high impact research. I think there was a question somewhere there.
My name is Aditya Chaudhary and I am from Mumbai. My question was that when a light ray travels from a rarer medium to a denser medium, what will happen to its frequency and the wavelength?
Okay, when light travels, so yeah, this is something that so the frequency changes when light travels from one medium to the other. I have to remember whether it is increasing or decreasing. Anyway, maybe I'll get back to you on that. Yeah, it's wavelength changes when it enters into a medium. Maybe I'm wrong. Yeah, sorry. But wavelength has to change. Yeah.
So I want to answer your question. Sorry. So the frequency remains same. That's why the color doesn't change. So if you pass a red light stays as red light. So wavelength changes. At the same time, you also have the speed of light changes. That's why the frequency stays constant. Yeah.
Thank you.
Yeah. So speed of light is wavelength into frequency, right? So if speed changes, then frequency remains same. Wavelength should change. Okay, more questions?
Actually, the wavelength doesn't change. The wavelength shouldn't change because otherwise the color would change.
Sure. Yeah, exactly. That's what I think Venki was describing.
Yeah, the frequency changes, not the wavelength. The wavelength would be what determines the color you perceive. So if the wavelength changed, then that would be a bigger problem.
Yeah, let's look at it. Yeah, probably a little bit more detail.